Hello everyone, this is Orlin from Learn Orlin. As always, you can email me or DM me on my socials for some more one-on-one tutoring. Feel free to schedule a consultation to see if we have a free consultation to see if we have anything that we can help you in. I'm a rising junior at UW studying computer science, and I also have uh, or I'm going for two minors in computational finance and applied mathematics. I'm also aiming to get my MBA. To begin, we have the reference string, which is essentially the program or process requesting each page of memory to use. So in our instance, we request page one, then three, then two, then three, then four, and etc. And each second we will see, depending on the algorithm, what our frames will look like during each request. And we'll start empty. This is a traditional three frame with extra here. We have an extra row here to decide if it was a hit or a miss, as denoted by a check or an X. But to begin, we'll start with FIFO. And since we're empty, there will be one, we'll just simply enter the frame. FIFO works as in first in, first out. So the first page to come in will be the first one out. And since we had to insert one, this is known as a page fault since it was never here. Now we move on to three. One, three. Again, three was not here, so a fault. So we have two faults. Now, one, three, two, because two was not here. Again, this would be a page fault. Now our next one, three, and two. And see how we have three in here? Will be a page hit because three's already in. You don't have to replace anything. So we're good. Now, next one, four. Four does not exist in our pages or in our frames. So we look at the one that was first in because that will be the one the first out. In our case, it is one. So we have four, three, two. That is the replacement of one. And it was a fault because four was not here. Next, we have three. Does three exist? Yes, it does. So this will be a hit. Looks good. Now zero does not exist. Which one would be replaced? I'm sure this is easy to tell. It would be three. With more complex, it's very easy to track. I like to look at to just go back one row at a time. So four we see goes here. Three we see goes all the way back here. And two doesn't go as far. So three is our one to replace. Four, zero, two. And that's a miss. Now eight does not exist. Which one to replace? It's like four goes to here, zero only here, two all the way back. So four, zero, eight. And it was a miss. So this is what our final frame will look like. And we can also calculate our hit rate and our fault rate. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8 frames. So fault rate and hit, oh my, hit rate, both over 8. And we just simply count. So we had 1, 2, 3, 4, 5, 6 faults and only 2 hits. So there we go. We have a 75% fault rate and a 25% hit rate. FIFO is generally the simplest, but also the worst. All right, next we have LRU, or least recently used. Pretty similar and easy to get tripped up with FIFO. So first we begin with entering one. We have one does not exist. So we insert one, we have a fault. Next, three, one, does, three does not exist. So another fault. Pretty similar to how FIFO, two is not in here. One, three, two. Now we fault. Next, three. We do have three. So this is a hit and our most recently used. Okay, next, four. Four does not exist. So we look and see what was the least recently used. Now you could do the similar trick of going looking all the way at the end, or we could use a sliding window. Now we're here at four. We search in the past three since we have three rows or three frames. Now we'll look three, two, three. Oh, it's not, it's a duplicate. So our sliding window, I know I said three, but we don't want to hold it as a list. We want to hold it as a set. So we should look at the difference between a set and a list is set can now have duplicates. So we want a size of three set. So three, two, three duplicate won't be in our set. Three, two, one. We get rid of one. It is also pretty easy to look back and tell. But similarly, we can't have one be used again because it's the least recently used. Four, three, two, four. Next, three, three in here again. Four, three, two. And since we had it, it's a hit. Next, zero. Now, if we were to do FIFO, let's look. Four goes back to here. Three all the way to back here. Two here. But the difference is it's the least recently used. So let's look at our sliding window set of three. Now look, three, four, no duplicate, two. Our least recently used is two. So we replace two with zero, and four and three remain. Now eight is going to be a miss. Where does eight go? We have, let's look back in our window, eight, zero, or eight, or zero, three, four. Four is the one to go. Don't even have to look back, just know my set. Eight, three, zero. Three was the most commonly used, or the least recently used is going to be the one to go. This ensures that when we make a request for the page, we don't get rid of what we aren't commonly using. So the hit rate, one, two, three, four, five, six, still not as good. It's still pretty similar to FIFO. It's a better idea, but does not outperform FIFO typically. Okay, the next algorithm we have is optimal. Optimal is more of a theory of the best way we can handle these page replacement algorithms, and all the other ones are compared to the performance of optimal. Because the way this one is, we cannot have it handled in real time since it looks ahead to know what would be the best um page to replace. So again, beginning, we insert one, empty, it's a miss. We insert three, three does not exist again, it's a miss or page fault. And now two does not exist, it's a miss or page fault. Next, three. is a hit since it already exists. Now we have 4. So we look ahead. We have 1. Is it used again? It is. Okay, 3, it will be used again. 2, 2 is never used, so we should not use it. And that will be the page to be replaced. This is more of a hypothetical algorithm. Next, we have 3. 3 exists, so it's a hit. Next, we have 0. So we look ahead. Which one is to be used again? We have 1, 3 never used again, 4 never used again. So since we looked at 3, we will replace it. It does not matter where which is to be replaced, since none is to be used again. But since we know 3 is more commonly used than 4, 3 is the most recently used, it would make sense to replace 4 instead. Next we have 1, and since we knew 1 was coming again, this time we had a hit. So we look at our hits, 3 hits, and a less of a fault rate. Right, there we go. Finally, we have the second chance algorithm. The second chance operates the same as FIFO at base, but we keep a bit that denotes our usage to know if we should give our page a second life. So to begin, it'll make sense as we go. To begin, we have 1. It's not here. It's a hit. Know how it goes. 1 does not exist. 1, 3, 2. Oh, I've been lazy. See, as we go, remember the binary bit, 0, 1. Since none have hit yet, they've all been misses. They don't have a second chance yet. But now we see 3. You know 3 is a hit since it exists. Instead of having the binary bit 0, it increments up. And it was a hit. Next we have 4. So, is 4 to leave? No. Or, sorry, 4 is to come in. Or 1, because it operates as a FIFO. And 4 is a 0. 3 is our still binary bit 1 and 2. Next, 3, a hit. And notice it incremented to 1, but it can only be at 1 because it's binary. We can't go to 2, 3, and so on. But it is a hit. Next, we have 0. Remember, it operates FIFO, so let's look. We have 4, 3, and 2. 3 is the farthest one back, so we got to remove it. But notice how we have the bit with the second chance. So instead of being removed, this is when the second chance comes in and it only goes down. Now we look again and we see which is to go. Is it 4 or 2? 2 is the one to go. So 2 gets replaced with 0. Now we have 1, which is to go in. 1 goes, 1 we check 4, goes to here. 3 all the way back here. 0 is only here. So 3 is to be replaced. It had the second chance, but it wasn't used again, so unfortunately it needs to be replaced. We look at our hit rate. It is only 2 out of 8, 25%. Fault rate 6 out of 8. Let me just do my bits here. Consistency. There we go.